Caspar Wessel's 1796 paper on the analytical representation of direction marks a pivotal, if initially overlooked, moment in the history of mathematics. This unassuming treatise, presented to the Royal Danish Academy of Sciences and Letters, laid the groundwork for the geometric interpretation of complex numbers, providing a visual and intuitive understanding of these abstract entities. Its significance extends far beyond mere visualization. Wessel's work offered a crucial step towards the acceptance and widespread use of complex numbers in various scientific and engineering disciplines. To appreciate the magnitude of Wessel's contribution, we must first consider the mathematical landscape of the late 18th century. While complex numbers, born out of the need to solve algebraic equations, had been around for centuries, they remained shrouded in mystery and regarded with suspicion by many mathematicians. The imaginary unit, the square root of -1, seemed to defy intuition and lacked a clear geometric interpretation. Prominent figures harbored reservations regarding the legitimacy of complex numbers. They were seen as clever tricks for solving equations, devoid of any real-world significance. Attempts at geometrically representing complex numbers existed, involving projecting them onto a line, thereby treating them as being analogous to the familiar system of real numbers. These interpretations, however, proved inadequate for grasping the richer algebraic properties of complex numbers, rendering operations like multiplication and division conceptually. Wessel's approach departed radically from these prior attempts. He recognized that a direction in the plane, relative to a fixed axis, could be represented by a complex number. This insight formed the cornerstone of his geometric interpretation. Specifically, he proposed representing a direction by a line segment emanating from the origin, possessing both length and angle. The length of the segment corresponded to the magnitude, or absolute value, of the complex number, while the angle it formed with the horizontal axis represented its argument. Wessel then defined addition and multiplication of these directed line segments geometrically. Addition followed the parallelogram law, mirroring vector addition. Multiplication, more significantly, involved multiplying the lengths of the segments and adding their angles. This elegant construction provided a clear visual representation of complex number arithmetic. The multiplication of two complex numbers resulted in another complex number whose magnitude equals the product of the original magnitudes and whose angle equals the sum of the original angles. The brilliance of Wessel's approach lay in its ability to provide a concrete meaning to complex number operations. The seemingly arbitrary rules of complex number arithmetic become transparent and geometrically intuitive. The multiplication of a complex number by the imaginary unit, for instance, corresponds to a counterclockwise rotation of 90 degrees. This geometric interpretation extended to more complex operations, allowing mathematicians to visualize and manipulate complex numbers with unprecedented ease. His work elegantly resolved the central problem, setting the understanding of complex numbers. He banished much of the suspicion surrounding them thanks to his provision of an intuitive geometric model. Wessel's formulation, using modern notation, began by letting the positive real unit, +1, be represented by the line segment, O of length 1, extending along the horizontal axis, and the positive imaginary unit, positive square root of -1, be represented by the line segment, O', again of length 1, extending along the vertical axis. Line segments situated in the opposite orientations, from O to A and O to A', represent -1 and the negative square root of -1, respectively. Wessel considered all directed line segments contained in the plane to be expressible in the form +b times the square root of -1, where and b are real numbers, and where the line segment extends from the origin O to the location specified by the coordinates A, B. The angle associated with the directed line segment is the angle formed by the line segment situated along the horizontal axis from O to A, namely the directed line segment corresponding to the positive real unit, +1, and the directed line segment of interest. Two directed line segments are equal if, and only if, they possess the same length and direction. He proceeded to develop rules for determining the number of units and the direction of the line segment that results from performing arithmetic operations like addition and multiplication on such directed line segments. The immediate impact of Wessel's work, however, proved minimal. Published in Danish, in a relatively obscure journal, his paper remained largely unnoticed by the wider mathematical community. This obscurity stemmed partly from the journal's limited circulation and partly from the fact that Wessel, a land surveyor by profession, lacked the academic prestige necessary to command immediate attention. His presentation, while rigorous, appears somewhat cumbersome by modern standards, possibly contributing to its difficulty in gaining traction. The mathematical world simply was not ready to embrace such a radical idea from such an unexpected source. Despite its initial neglect, Wessel's paper eventually resurfaced and gained recognition as a foundational work in complex analysis. Decades later, independent discoveries of the geometric interpretation of complex numbers were made by Jean Robert Argand in 1906 and Carl Friedrich Gauss, who published his findings in 1931. Gauss' endorsement, in particular, played a crucial role in popularizing the geometric representation, sometimes referred to as the Argand diagram or the Gauss plane, even though Wessel predated both. Interestingly, some argue that Gauss had developed similar ideas even before Wessel, but chose to delay publication. This illustrates the complex interplay of intellectual history, priority disputes, gradual acceptance of groundbreaking. The subsequent development of complex analysis owes a considerable debt to Wessel's initial insights. His geometric interpretation provided a visual framework for understanding complex functions, complex differentiation, and complex integration. It became an indispensable tool for mathematicians and physicists alike. Complex analysis found widespread applications in diverse fields, including fluid dynamics, electromagnetism, quantum mechanics, and signal processing. It is challenging to imagine these fields progressing without the foundation laid by the geometric interpretation of complex numbers. Wessel's work also foreshadowed the development of vector algebra. His geometric treatment of complex numbers, defining addition via the parallelogram law, anticipates later formalizations of vector spaces and linear algebra. While Wessel did not explicitly develop the concept of vectors as independent entities, his work demonstrated the power of geometric reasoning in algebraic contexts. He thereby provided a crucial stepping stone towards the modern understanding of vector spaces. It is also interesting to consider the philosophical implications of Wessel's work. By providing a geometric representation of imaginary numbers, Wessel helped to bridge the gap between the abstract world of mathematics and the concrete world of spatial intuition. The imaginary ceased to be purely abstract. This fostered a deeper appreciation for the power of mathematical abstraction and its ability to capture and model real-world phenomena. One may ponder what drove Wessel, a surveyor, to tackle such a fundamental problem in mathematics. Perhaps his work as a surveyor, dealing with angles and distances, provided him with an intuitive understanding of geometric relationships. Perhaps the challenge of representing directions analytically, a practical necessity in surveying, led him to explore the deeper mathematical implications of the problem. Regardless of his motivation, Wessel's achievement stands as a testament to the power of interdisciplinary thinking and the ability of individuals outside the established academic circles to make profound contributions to knowledge. The influence of Wessel's work extends even to contemporary mathematics and physics. Concepts like phase and amplitude, which are central to wave phenomena in both classical and quantum mechanics, are directly related to the geometric representation of complex numbers. Signal processing techniques, such as Fourier analysis, rely heavily on complex exponentials, which are best understood through their geometric interpretation as rotations in the complex plane. Even in areas such as control theory, where the stability of systems is analyzed, complex numbers and their geometric representation play a crucial role. The story of Caspar Wessel and his paper on the analytical representation of direction delivers a compelling lesson in the history of science. It demonstrates how groundbreaking ideas can be initially overlooked and how their ultimate recognition can be a slow and circuitous process. It highlights the importance of independent verification and the role of influential figures in promoting novel concepts. Furthermore, it reminds us that significant contributions can arise from unexpected sources, challenging the notion that innovation is the sole domain of established academics. Wessel's 1796 paper serves as a potent reminder that the pursuit of knowledge knows no boundaries and that even the simplest of problems can lead to profound and far-reaching discoveries. His work, initially relegated to obscurity, ultimately secured its place as a cornerstone of modern mathematics and its applications. This represents an enduring legacy, a subtle yet substantial reshaping of the mathematical landscape.